All right. Let me just today get right into it so we can um, get through with stress, maybe get through with strain, and then uh, you'll be ready to work on some problems. Um, we finished last time by talking about this relationship that said the stress tensor multiplied by a unit normal that points out of a face is equal to the traction vector. So n is the outward normal to the face. T is the traction vector on the face. And sigma is the stress tensor, like it always is. There's two ways you can use this. Two ways you could use this. One ends up being a lot more useful than the other. So the first one is if you know the stress tensor. Actually, let me go in the other order. The first one is if you know that is the one I want. If you, that's my final answer. If you know the stress tensor at a point, this lets you calculate the traction on a chosen face at that point. So the traction at that point on a chosen face. Stress tensor always refers to a single point. Yep. Yep, that's right. So that 3x3 matrix, the stress tensor, represents a single point. All of those values represent a single point. This isn't usually that useful because usually easier to measure the traction on a face than it is to measure the stress tensor. Although there are times that we'll use this. And the second way to use this is if you know the traction on a face, it puts limits on the allowable stress tensor at that point. Let's say it puts limits on what stress tensor values are allowable. So this is the one that ends up being more useful most of the time in continuum mechanics. So I'm going to do an example of each of these. first, let's say that we have a material like this. I think I drew this one at the end of class last time. So let's say this is the object viewed from the side, and we'll use a coordinate system like this. This angle is 45 degrees. And let's say at points on that surface, the stress tensor is equal to 2, 0, 1, 0, negative 5, 0, 1, 0, 8. And that's in megapascals. That one, each of these is 1 times 10 to the 6 pascals. And based on that, we want to figure out what are the distributed loads on that surface. Well, to figure out what the outward facing normal is, here's the coordinate system. And I'm going to draw a vector like this that's parallel to the face. We know this angle is 45 degrees. And an outward facing normal is perpendicular to that. This is what we're trying to find. That's the outward facing normal we're trying to find. So the angle for that outward facing normal is, go from the positive x-axis to here is 135 degrees, then backtrack 90. So this is at positive 45 degrees. So theta is 45. And that means that the outward facing normal is cosine of 45, sine of 45, and we're doing all of these problems in 3D. So this just has 0 z, nothing's happening in the z direction. 0.7071, 0.70710. Yeah, it's a unit vector. All right, so then to calculate the traction is equal to the stress tensor times the outward facing normal. So that's 2 times 10 to the 6, 0, 1 times 10 to the 6, 0, negative 5 times 10 to the 6, 0, 1, 1 times 10 to the 6, 0, positive 8 times 10 to the 6. And we're multiplying that by the outward facing normal. And the vector you get out of that is 1.414 times 10 to the 6, negative 3.535 times 10 to the 6, and 0.7071 times 10 to the 6 pascals. So if we know the stress tensor for points on the face, this tells us the actual loading occurring on the face. And that's pretty interesting because this is sort of where external loads on the object meet the internal loads that are represented by the stresses. Okay, that says that if this is not the total external loading happening on that surface, on that face, that stress tensor I gave you can't be the actual stress tensor. Yeah, if we somehow know that this is the stress tensor for points on the face, that means that these have to be the component of traction on the face. That has to perfectly describe the loading on that face. Okay. Any other questions about that? It's going to generally be large because, like I said, this the reason you use this stuff is to figure out when engineering materials are going to fail. And for engineering materials to fail, you have to put pretty big loads on them. So yeah, they're going to be big values. If there's no reason they have to be big values, but if they're not, then you don't bother with this kind of analysis. You know nothing's going to break. So now the other way, and this is generally more useful because what's easier to measure, stress going on inside, the internal stresses going on inside a body, or the external loads being applied. Measuring external loads is easy. You put load cells in and whatever. So this is a way to measure the external loading and then figure out based on that what restrictions are on the stress tensor. The traction is, yes, it's distributed loads, distributed over an area. But other than that, yes. So it's not point forces. It's force per unit area happening at a point. Okay, so let's say that the body is this rectangular solid. I guess it has a square cross section. Height is 0.1 meters. And its dimension is also 0.1 meters. And let's say that there's a uniform distributed load applied to the front. That's all facing in that direction. It has a total force value of 25,000 newtons. And the question is, what restrictions does this put on the stress tensors for points on the end? So how does this loading restrict stress tensors representing that face? Well, that force, the total force vector, that 25,000 Newton force is acting in the negative x direction. So that force is just negative 25,000, 0, 0 in newtons. That's not a traction. Traction has to be force per area. So we'll divide by the face's area. To get the traction. The area is 0.1 meters times 0.1 meters, so 0.01 meters. And now we can just divide each one of these components simplify this to get the traction vector. So the traction vector is 2.5 times 10 to the 6 negative 0, 0 in units of pascals. Any questions about getting that traction vector? Okay, so now we know that that traction vector is equal to the stress tensor times the outward facing normal. So negative 2.5 times 10 to the 6 is equal to, and I'm going to start with a general stress tensor. We don't know anything yet. So xx, xy, xz, xy, yy, yz, xz, yz, zz. And what's a unit vector that's pointing directly out of that face? Yep, positive 1, 0, 0. And now we just go through the matrix multiplication. And we have one equation that says negative 2.5 times 10 to the 6 is equal to 1 times sigma xx. Um, 0 is equal to sigma xy, and 0 is equal to sigma xz. Yep. So what we're looking for is a unit vector that is perpendicular to the face you're looking at, going from the material out of the material. So in that case, it's going directly this way, and directly that way is in the positive x direction. And then it's a unit vector, so it has to be 1, 0, 0.
Is it the n vector?
That's the n hat, yep. All right, so what we have now is this gives us the ability to restrict some of this stuff. The stress tensor, we know that the first value, sigma xx, is negative 2.5 times 10 to the 6. We know xy is 0, xz is 0. And with symmetry, we know these are 0 then too. We don't know anything about sigma yy or sigma yz or sigma zz. So this wasn't enough information for us to fully define the stress tensor, but we learned a lot more about it. And these are boundary conditions that you can use if you're going to try to solve this problem as a differential equation. You know that loading that was given only gives these options for a stress tensor. You know, these three independent values can be anything, but 3 of these values are fully defined. Yep.
Like, why is it like why is it 0, 0 and 0, 0?
Where did we get this stuff?
It's just a 0, 0. Is this supposed to be also like sigma x, y, sigma x, z over 0?
Yeah, that's what this is. So this is sigma xy, this is sigma xy.
Oh,
This is xz, and this is
okay,
xz.
so
Because of the symmetry, yeah. Okay, in this class, we're not, so this is a really important idea as you get later into this stuff. In this class, we're not going to use this much, but there's one thing that we're going to use this fact for. So the one thing that we'll use this for in D form is defining the principal stresses. Which kind of principle is this? Yeah, this is, and when I say principal stresses, I mean the vice principal stresses. Yeah, it's your pal. Finding the principal stresses. So that's going to be a big topic later. What? That's always a big topic. You know, there's two ways to write principal. Maybe you hadn't thought about that before. Okay. Okay, good. So that's about all we're going to say about the definition of stress. So now we can talk about strain. The second most important quantity in this class.
Are we kind of like easing into criteria, or is this like kind of a subset of different criteria?
Well, so stress is, so we're going to define what's happening at a point inside a body by two things. Stress is how we're going to measure the loading at that point, and strain is how we're going to measure the deformation, the local deformation at that point. So stress is a measure of internal loading at a point. This is one of those comparing, contrasting type things. This is a measure of internal loading at a point. So the key is stress is loading, and strain is a measure of local deformation at a point. And all of the problems that we're going to do in this class depend on a linear relationship between the stress and the strain. There's always a linear relationship between stress and strain. Material or in a loading environment where there's a linear relationship between stress and strain, called a Hookean material. And that's because you know, that linear relationship between loading and deformation that you have in springs, that's called Hooke's law. We have the same thing happening here. It's going to be more complicated because instead of a single constant of proportionality, we're going to have a matrix of proportionality, but it's going to be a constant matrix, so we call it Hookean.
So it's constant? Is that the same as linear?
So it's constant is like with springs, you have that the force is equal to kx, and it's linear because this is a constant. And what we're going to have that strain is equal to a big matrix, the compliance matrix, times the stress. And the relationship is linear because the elements of that compliance matrix are all constants, the same way that this K is a constant. What? Okay. What? Yeah, we'll use this all the time, yeah. You definitely want this programmed into your calculator because this matrix is 6 by 6. This is going to be a 6-element vector, and you do not want to be. We're going to do a lot of these, and you're not going to want to do them by hand. Okay. Yes. Well, actually, on D2L in the course information, there's a list of programs that tells you how to do it on an 89. And if you have anything other than the 89, then just come talk to me and I'll help you translate it. And yes, I know it seems sort of arbitrary, like an 89 is not, it's like not the oldest one, it's not the newest one, it's just somewhere in the middle, it's just the one I have. So it made it easier for me to write out that sheet. One thing to remember as we're going through strains is that the methods in this class, methods in D form, are relevant for small deformations. That means length changes of less than about 0.01% of the object's length, and strain values, I said greater than. No, that doesn't make any sense. Less than. And strain values less than about 1 times 10 to the minus 4. Yeah, well, I haven't defined strain yet, so it'll make more sense when I talk about that. But I'm just saying this because as I go through examples, as I draw pictures and go through example problems with strain, my examples are always going to have deformations much, much bigger than this. So just be aware that for these, like mathematically, you can do the math with anything, but for this to be physically meaningful, you have to have very small length changes due to deformation. Okay. My examples will often show deformations much bigger than those. Well, yeah, but you have to analyze it differently. One of the things that's, so let me draw one picture and then I can talk about that a little more.
At a certain point, the material is still past where it can come back to its
That's right.
shape.
Yeah, that's right. And there's a pretty good correlation between the range of where materials stop being linear, engineering materials stop having that linear relationship, and where they stop doing what you're talking about, being elastic and returning to their original shape. Those really are, there's no reason those have to correlate to each other. Those are two different things, but they tend to be roughly the same regions, you know. So if you go past the point of permanent deformation, you've probably also gone past the point of linear relationship between stress and strain and vice versa. Okay, so here are the deformations that we're going to see. If this is a cube that represents the reference shape of like a local neighborhood of a point, after the deformation, there are going to be angle changes, and length changes. So objects that are initially a cube after the deformation become a parallelepiped. Remember that? That was on the SATs probably. It it means that it's an object where every face is a parallelogram. But anyways, I drew this picture because there are two things that happened in deforming this to this. Lengths changed and angles changed. And mathematically, one of the reasons that, so like what if there was a material, so most materials, almost any material I can think of, the range of deformations where the relationship between stress and strain stays linear is pretty small. Once you deform it even a noticeable amount, like to the naked eye, it's already out of that linear range. But you could imagine, maybe somewhere there's a material that you could smush all the way in half and it's still a linear relationship. Why not, But one of the reasons that we wouldn't be able to, that even with a material like that, our calculations wouldn't work, is because of those angle changes. We're going to assume that all of these angle changes are small. And so, like for example, the length of one of these edges is the same as the height of the surface. We're going to throw out those angle changes in sort of like small angle approximations. And so the math would have to get a lot more complicated if you had significant angle changes. Why did I talk about that? I don't know. What?
You have like piece of materials, is there like external load, just like steel? Is there stress also acting on it?
When it's just sitting there?
Yeah, just sitting there without like anything, like nothing on top of it.
Nope. Right. There's weight causing small stresses, but yeah. Like out in outer space, there's no stresses. Yeah. And just like stresses, strains can be broken up into normal strains and what's the second one? Shear strains. Shear forces, yep. It's not really the same thing, but they are related, and we'll talk about like as we go on, we'll see the relationship between those. Normal strains have to do with length changes. and shear strains have to do with angle changes. Okay, so I'm going to talk about normal strains first and then shear strains. So let's say we have a deformation of, this is really infinitesimal, but we'll treat it as a really small cube, where the coordinate system is oriented like this, with the z-axis out, and the undeformed lengths, let's call capital L sub 0. And after the deformation, we have something like that, where the length along the x-axis I'll call lowercase l sub x, and the length along the y-axis lowercase l sub y. And picture that this is an example. The picture I drew is way, way, way outside of the size of deformation that's allowable mathematically for us. If I really tried to draw it down to the 100th of a percent, it wouldn't be very convincing. No, nope. No, you can't look at it and tell the difference. So the x normal strain that we'll call epsilon xx is equal to the deformed length along the x-axis minus the initial length divided by the initial length. And another way you can think of that is that deformed length minus the initial length is a change in length, so you could think of it as the change in length along the x-axis divided by the original. Yeah, delta. And then epsilon yy, you do the same way, but it's just the deformed length along the y-axis minus L sub 0 divided by L sub 0. You can also think of that as delta y over L sub 0. And in my picture, you couldn't see what's happening in the z direction, but it works the same in the z direction. Epsilon zz is equal to lowercase lz minus L sub 0 divided by L sub 0, or delta z over L sub 0. Yeah, right. And in problems in practice, you will have to do that. So you would just use the initial length of the x side, the initial length of the y side. Yep. I'll do examples like that. So what does it mean, looking at these formulas, if you have a normal strain that's positive? That's right. So positive normal strain means it's stretched, the length increases. And negative normal strain means contracted. Do you remember what it means with normal stresses if you have a positive normal stress? If you have a positive normal stress, it means that along that axis, the thing is in tension, being pulled apart. And if you have a negative normal stress, it means it's in compression. So there's like a natural relationship between positive strain and positive stress, or negative strain and negative stress. You see that like if you pull something apart, it stretches. If you push it together, it contracts. Okay, let me do an example. So let's say we have a material that starts out with a height of 0.008 meters and a width of 0.01 meters. And we'll use a coordinate system with the y-axis up and the z-axis to the left. And under deformation, we end up with a thing that has a width of 0.005 meters, a height of 0.011 meters, and no change in the out of plane thickness.
That coordinate system, that rectangle, I feel like there's
You could have any two axes can be anyway, and then they specify the third one. So what that is saying is that the x-axis has to be coming towards us.
oh yeah.
It's worth it though. That's what happened to Aaron. Yeah. Ah! I'm going to edit that out of the video. Okay, so what are the normal strains? So first, we'll just go in the order XX, YY, ZZ. So XX, we have some thickness. We don't know what it is. I'll say, let's say that the original object had a thickness into the page of capital L. Okay, and it said that that thickness doesn't change after the deformation. So we just have L minus L over L equals 0. So that's just saying there's no deformation along the x-axis. Along the y-axis, we have a new length of 0.011, an initial length of 0.008, divided by the initial length of 0.008. And these are all, everything's in meters. The meters all cancel out, and so when you divide that, you get 375. And then for ZZ, you have a final length along the z-axis of 0.005 minus the initial of 0.01 divided by 0.01, and you get a value of negative 0.5. So this one is stretched. This one is contracted. And this one is no deformation. How do these values compare to our criteria for small deformations? Way, way too big, by a factor of 10,000 or something. But mathematically, that's how you do the calculation. And let me say one more thing, and then we're done. Notice that strain has no units. Strain is unitless. Because you have something measured in length divided by something else measured in length, the units cancel out.
So how do you know if it's something formed like any like material? How do you know that the change in length is very, very small?
How do you know that you have an allowable? The only way you know that is based on careful analysis of that material. And obviously that's already been done for most materials, but you would need to figure out for steel what's a range of stress values where this approach is still good, and then you'd use that information in your calculations. Yeah, so I tend to think of it as like the same way you think of force as what causes a deformation on a spring. Think of stress as being what causes a strain in an object. It's the load that causes the deformation. I think that's a reasonable way to think of it. Any other questions? Okay. Have a good weekend.